How many people are usually on here?
Somewhere between 10 and 60. It depends on the day, really.
Okay. Just looking at some of the names, it looks like you're well represented by people from all over the place.
Yeah, that's usually the case. I suppose most people here are from Imperial College, though.
Yeah, Imperial. I'd say Imperial is the most international university in the UK. I think in Europe, in fact. I think about 40% of Imperial College's studentship is international, as in not from the UK.
Okay.
All right, I think.
Believe it.
Yeah, sorry. I think now the YouTube is working as well, so now we can make a start. Thank you so much for your patience. So, hello everyone. Thank you all for coming. Today we have a very exciting talk, but before we start, I just want to highlight that this meeting is being recorded and will also be streamed on YouTube. So by joining, you give consent to this. Today we have been joined by Professor William Emrich, who's an ex-engineer at the NASA Marshall Space Flight Center. He designed and led the NTREES nuclear thermal hydraulic rig, which is used to test the performance of nuclear fuel for the nuclear thermal propulsion systems. We are very happy to have him with us today, and Professor Emrich, the floor is all yours.
Okay. Let me see if I can get my screen up. Okay. You're going to have to let me share my screen here.
Yeah, I'll make that work.
I don't do this all the time, so every time I do it, I have to kind of figure out how to start showing everything.
Yeah, now you should be able to.
Okay. Okay. Yes. Let's see. Let's get this out of the way. Okay. Can everybody see this?
Yes, we can see it.
All right. So I titled this the challenges, promises and challenges of nuclear propulsion for space travel. And I'm not sure exactly what you, how much everybody knows about the subject. It's something I've been involved with for quite a number of years, and hope to still be for some years ahead. So we can, hopefully you'll find this interesting. Let's see. And okay. Okay, so first I'd like to talk a little bit about where I came from. Deb asked me this question just a minute ago, so I will try to answer where I'm from. So I'm from the United States, in the state of Alabama, which you see highlighted there. And so it's a state, it's about 200 miles or across, about 400 miles in length. And actually, I'm from Huntsville, Alabama, which is called the Rocket City. And it's the home of NASA's Marshall Space Flight Center. And you can see an aerial view, kind of what it looks like when you come into our town. The very first thing you see from the distance is a Saturn V rocket. That's our, we developed that rocket here at this center. And we have mostly, the one here standing up is not actually a real one. It was, although it does have real engines in it. Our real one is actually down here in the lower right-hand corner, where it says Davidson Center for Space Exploration. Here we have a big Saturn V rocket on its side, which you can look in a lot of detail, and it's quite impressive. And actually, this city was it wasn't started by Werner von Braun, but he and his team came here from Peenemünde and was our first director at the Spaceflight Center here. And actually, as an aside, I'm currently teaching nuclear rocket propulsion at the University of Alabama in Huntsville. And he actually started that school while he was here. And this is some of my family, my son and his wife, in front of the Saturn V. So you can see it's pretty tall, about a 36-story building. So anyway, that's a little bit about me and where I come from. So with that, I'd like to show you, here is the United States actually did nuclear rocket testing back in the 1960s and 1970s. And there's a little test that they ran. And I thought you might be interested in seeing what a test looked like. You should see a plume of gas coming up, and it should be, you'll see what a test looked like. So we're counting down, 2, 1, and fire. And so it should start here. And say, oh my goodness. I am so sorry. This was not supposed to happen. I just applied. I have no idea how this got in my presentation. These nuclear rocket engines are not supposed to explode like this. They're supposed to be just normal rocket engines firing. And here, I'm sorry you had to see this. Oh my goodness. Well, I hope the people are okay. Looks like they're running away. That's good. Hopefully they'll be. Oh my, what are they doing? They're picking up radioactive material, just what do they think they're doing? Tell you, actually, this was a planned test. It's called the transient nuclear test, or TNT test. And they wanted to see if they could make a nuclear rocket explode. And they were able to do it. But they had to do a lot of disabling of their safety systems and everything to make it blow apart like that. But you can see it would be a bad day if something like this happened on a spaceship going to Mars or something like that. But anyway, just as an introduction. Okay, let's have some preliminaries first. Okay, so why would we want to use a dangerous nuclear rocket engine over a much safer chemical engine? Because we all know nothing bad can happen with chemical engines, right? Well, for one, if astronauts are going to travel to Mars or any other place in the solar system in any really practical sense, you need something better than a chemical rocket engine. They just don't have enough energy in them. The chemical bonds you just can't do it, or at least not very easily. Nuclear rockets, on the other hand, you don't have constraints to their amount of energy available. They have a virtually unlimited amounts of energy. A typical manned mission to Mars would require, again, the fissioning of only about 150 grams of uranium. And that's to power a very large spaceship through all its maneuvers to and from Mars. And as you can imagine, you need other equipment besides just this 150 grams of uranium. But it is something that, just to give you an idea of the power density that you can get from uranium. The constraints, though, you still have some constraints on nuclear engines. And they really have to do not so much with the amount of energy that is available, but how fast you can transfer this energy to the propellant. So nuclear engines, rather than being energy limited, are power density limited. And this energy rate at which you can transfer the power is mainly limited by the maximum temperature which the uranium fuel can understand. And so a lot of the effort these days is trying to find uranium material combinations which can withstand very high temperatures. So what are the engine configurations which we have? Well, conceptually, really, engines are really simple. They just involve a nuclear reactor, and it heats propellant like hydrogen to really high temperatures and then expels it through a nozzle. This is what's called the hot bleed cycle. It's the one which was used in all the testing which was done in the United States back in the 60s and 70s. And you can see it, you have propellant, it goes through a pump, comes out liquid hydrogen and comes down, it goes around the reactor where it turns into a gas, and the flow splits a little, usually it splits, with the majority going through the reactor, and where it's heated to around 2800 Kelvin. Some of it is siphoned off, and it, along with the rest of the propellant, goes into a turbine and is then expelled. The turbine is the energy which runs the pump. So it's a fairly simple cycle, but it was used quite effectively. The other is an expander cycle. It's a little bit more complicated, but if you notice on the hot bleed cycle, going from the effluent from the turbine is just dumped overboard. So you're really wasting some of your propellant. On an expander cycle, the effluent from the turbine is directed back into the reactor, where it's heated to really high temperatures for and used that way. So expander cycle is more complicated, but it's also more efficient. Now, to determine the performance of the engine, it's necessary to define a parameter called specific impulse. And specific impulse is mainly a means to evaluate the efficiency of a rocket engine, nuclear or otherwise, and it's analogous to the liters per 100 kilometers for an automobile. I'm used to saying miles per gallon, but that's I imagine over in Europe it's liters per kilometer. And it's since this is a rocket society I'm speaking to, I imagine most of you probably already know what specific impulse is. Anyway, it's specific impulse is calculated by dividing the rocket thrust in newtons by the propellant flow rate, and it has units of seconds and physically represents the length of time that a rocket engine can produce 1 Newton of thrust from 1 kilogram of propellant. So it can also, through some little thermodynamic derivation, you can see that the specific impulse is a function of the square root of the temperature. So you want high temperatures to get that specific impulse up, and molecular weight, it's divided by molecular weight. So you want a low molecular weight and a high temperature, gas temperature. So those are, so that's one of the main equations that we use to evaluate how good these engines are. The other, excuse me, is the rocket equation, and it yields the maximum velocity increment attainable by the space vehicle. And it's proportional to the specific impulse, which you would have gotten from that previous equation, by the log of the mass fraction. So MF is basically the empty weight of the spacecraft, and M0 is the fueled weight. So empty weight divided by fuel weight times the log of that times the specific impulse. And that gives you the exhaust velocity. So how does it compare to other engines, a nuclear engine? Well, let's look at a chemical engine first. This is a hydrogen oxygen engine that the space shuttle used. It's very efficient of these engines. And the equivalent molecular weight of the effluent from the rocket was about 10. It had a nozzle ratio of 77. That is the area between the throat area of the nozzle and the exit area of the nozzle. It's about 77. This chamber, area of the chamber over the area of the throat really doesn't have too much effect in most cases, but it was about 10. And then the specific heat of the steam from the hydrogen and oxygen has a specific heat ratio of about 1.33. And the exhaust comes out at around 3,600 Kelvin. So you can see from this plot that gives you a specific impulse of roughly 460 seconds, which is pretty good for an engine. Let's look at a nuclear engine now. So here, instead of having a molecular weight of about 10, we have a molecular weight of about 2. And it had a 200, since it's going to be operated in space, a nozzle area ratio of around 200, again, 10 for the area of the chamber in the throat. Here, the specific heat ratio of hydrogen is about 1.4. And actually, about the best you can do, maybe a little better, is about 3,000 degrees for the exhaust. But note that it gives you a specific impulse of about over 900 seconds. So roughly twice as good as chemical engines. And that is almost entirely due to the molecular weight as opposed to the temperature. The temperature is actually lower than the chemical engine, but you more than make up for it by the molecular weight of the hydrogen. So what does the rocket equation tell us? So we want to translate its efficiency into interplanetary mission characteristics. So every space mission that you do, at least to another planet, requires a series of velocity increments. Remember, I said that the rocket equation gives you the total velocity that the spacecraft could reach. But actually, what you're doing is you break that total velocity up into velocity increments, which are used to meet the particular mission that you're doing. Now, for a round-trip interplanetary mission, this velocity change is divided into 4 major velocity increments: Earth departure, destination capture, destination departure, and Earth capture. And so let's look at what a Mars mission could do if you only use a chemical engine. Well, so here we have a mission to Mars. And if you assume the lowest possible energy for a Mars mission, it's called a Holman transfer. That's the lowest energy transfer that you can get from one planet to another. And so you need a velocity increment of about a little over 11.4 kilometers per second. And again, that has to be divided into those 4 velocity increments, which Earth departure, destinate Mars capture, and so forth. Now, as far as the length of time, it's a pretty long travel. That's if you do this Holman transfer, it takes about 259 days to get to Mars. So that's a long time to be cooped up. But if we assume that a chemical engine with about 450 seconds is used to get that velocity increment, you can have a mass fraction of no more than about 0.075. And that is very hard to achieve. That's you've got virtually all your mass is tied up into propellant. You have very little margin for the spacecraft, for the engines, for the tanks, place where people are going to live, the habitat, landers, what have you. It's very hard to achieve this mass fraction. That's why chemical engines to Mars are very difficult. Now, if you use a nuclear engine, so here is what you have. You can get there. You don't have to do that low energy Holman transfer. You can do faster trips. We assume that we have a nuclear engine with a specific impulse of about 900 seconds. You could accomplish the same mission, that is, if you did use a Holman transfer, with a mass fraction of about 0.27. And this is a much easier vehicle to construct. You remember you had very little mass fraction available before. 0.275 is not hard to achieve at all. But if you have a little better mass fraction than that, say 0.15, which is what often considered to be about the least that you can have on a spacecraft, you would be able to get to Mars in about 161 days. So you save yourself roughly 90 days of trip time each way by using this nuclear engine, and also on a more practical spacecraft. If you could make the mass fraction that you had on the for the chemical engine, you would be able to get to Mars in only 124 days. So nuclear rockets can really save you a lot of headaches as far as getting between Earth and Mars. So what are the challenges to developing a nuclear rocket engine? And there are a number. So we noted that the efficiency of most rocket engines is constrained by the fact that they're power limited. So you also have the what you have to do is to determine the best way then is to maximize the rate at which you can get this energy out of the fuel. Again, since they're power limited, how do you do it? How do you get that energy out in the best possible way? So from heat transfer considerations, as I mentioned earlier, it's chiefly limited by the maximum fuel temperature that you can operate the fuel at. And also, if you want to have a compact system, you want to have something that you have lots of surface area for a specific volume of fuel so that you can get the heat out more easily. So what specific challenges do we need? Well, nuclear engines have to be lightweight. Again, that mass fraction is a big driver in what you can do with these engines. So what that generally implies is you would like to use probably a thermal reactor with a minimal amount of uranium. Thermal reactors have generally light moderating material. Uranium, on the other hand, is very dense, so you can limit the amount of uranium in these engines. You can make them lighter. And so a lot has to do with configuring what's the best fraction of fuel to moderator. I'm not sure how much you all know about reactors, but anyway, moderating is something that you can do. You can put a light material in there, such as beryllium or carbon, which basically what it does is it helps use the fuel more efficiently. The reactor has to operate at really high temperatures. Well, high temperatures generally require the fuel to be a ceramic and that has a high melting point. But unfortunately, there has some nuclear characteristics often which don't really allow for moderating the fuel a lot. So generally, what you have to do is operate a fast reactor. And again, a fast reactor has very little moderator in it. So to be light, you want a lot of moderator. To be able to operate at high temperatures, you want very little moderator. Fuel must have high thermal conductivity. So you want to be able, again, you want to be able to get the energy out easily. So you don't want to have a low thermal conductivity, which means that your propellant temperature is low and your fuel is at high temperature. You want to have high thermal conductivity so the temperature difference between the propellant and the temperature can be relatively low. And so in this regard, generally you don't want a ceramic. You want something that's metal or carbon based. So again, you have all these trade-offs. For high melting point, you want ceramics. For high thermal conductivity, you want metals. The fuel must be able to resist the corrosive effects of high temperature hydrogen. Hydrogen at high temperatures can be very corrosive. So in this case, metals and ceramic work well, but carbon, which you would like to use for a moderator, is often subject to aggressive attack by the hot hydrogen. So if you do have graphite or carbon in the reactor, you have to isolate it from the hydrogen propellant. And that requires coatings, which can be problematic sometimes. The fuel elements have to be rugged. They're going to be subject to all sorts of vibrations and so forth, temperature gradients. And in this case, metallic and cermet fuel elements, although they have a lower temperature capability, are more ductile and crack resistant as compared to the ceramic. So what am I trying to say? Also, yeah, one need to have a high fuel surface to volume ratio. And so short heat transfer paths, and to allow for large amounts of heat to get transferred to the propellant in a small volume. So bottom line is, it's a big optimization problem. You have it's hard to know ahead of time just what the fuel needs to be made of, how it needs to be configured, all places where there's lots of research going on. So how do we address these challenges? Well, testing, 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 and more testing. So lots of factors to consider. So you can do lots of analysis, but really the bottom line is after the analysis is done, you still have to test everything. So all these competing factors, it's as I said, a giant optimization problem. So the types of testing that we can do are the most basic testing is materials testing. Here we can test small samples of the candidate materials and subject them to high temperatures, high pressures, and exposure to hydrogen, all conditions which they're likely to be exposed to. This type of testing can be done on a really small scale, and it's pretty inexpensive to do, but it's where you need to start. After that, you can do component testing, where you test individual fuel elements, pieces of uranium in different configurations. You want to test them again with regard to pressures and temperatures, but you want to expose them to different flow rates, vibrations, temperature distributions, which are more characteristic of what they would counter during an engine operation. This is also relatively inexpensive, but it's more expensive than simple materials testing. And this is what I was mostly involved with when I developed the NTREES facility, which I'll talk about shortly, but it's a facility to do component testing. And we were able to do a lot of very good tests at the relatively inexpensive. You do probably at some point have to do nuclear testing of these components, but it's once you start doing that, nuclear tests tend to be much more expensive. But still, if it's a small piece of a small fuel element, or it's not too bad. And then finally, you do full-scale testing. Here you have to test an entire reactor and engine system tested to prototypic conditions, and you need to capture the exhaust. This is a very expensive test, and it requires probably hundreds of millions of dollars to test under these types of conditions. But we'll talk about that a little more in just a minute. First, I want to talk about the engine program that the United States had in the 1960s and 1970s. It was called the NTREES program, which stood for Nuclear Engine for Rocket Vehicle Applications. And this is what it looked like. This you had a man standing there. He would come up to about the bottom of that reactor there. So these are not really huge systems. This was a hot bleed cycle. You see these nozzles, little nozzles up above the main nozzle. That's where the exhaust from the where they exhausted the propellant from the turbine turbopump system. And here's what the fuel looked like. They were basically hexagonal elements with 19 holes drilled in them. The diameter of these elements is about 2 to 3 centimeters flat to flat, and they were roughly 1.5 meters long. And so you had hundreds or even thousands of these, depending upon the size of the reactor. Some of the reactors were very large. Probably we would not make them quite so large today. For safety reasons, you don't want to have just one engine. You would probably like 3 or 4 engines for redundancy. We have here at the coming into town, we had a rocket park where they displayed different rocket engines. You saw the Saturn V on the first slide. Well, I saw this engine that they in the rocket park a number of years ago, and I was really surprised that they had a nuclear rocket engine there. And when I asked the people at this rocket park or museum, they said, well, they didn't really know what this was. But they had it, and so I asked if they could loan it to the Marshall Space Flight Center, and they said sure. This didn't seem very impressive to them compared to some of the chemical engines. So this was sitting right outside my office when I was working at NASA, and they cleaned it up some, and so we're very proud to say we have a NERVA rocket engine right outside our building. So the testing which was done for this NERVA system was done out in the desert. You see here was what was called the EMAD building, which stood for Engine Maintenance Assembly and Disassembly. This is where they kind of put the whole engine together. They integrated the nuclear reactor with pumps and all the other equipment that was done in this building. And they also had what was called the Reactor Maintenance Assembly and Disassembly building, the RMAD building. And that's where they just looked at the reactor itself, not all the other ancillary equipment. So this was all done out in the desert in a little place called Jackass Flats, Nevada. And it was home to scorpions, rattlesnakes, and just a few PhDs. And this is where that was done. It was done in Nevada, which in the United States, this is where Nevada is. You see the NRDS, that's the Nuclear Rocket Development Station. You can see it's just a little bit northwest of Las Vegas. And so that's where a lot of that testing was done. And here is a legitimate rocket engine test. And so I'll just show that. So this was some video which was shot back when they were doing the NERVA test. You see people looking at something or other. And so there's a reactor. You see it's not really that big. It's about 6 feet across. And there you see all the little elements, fuel elements in there. Here is an aerial view of the Nuclear Rocket Development Station. And there you see a nuclear rocket engine test. So that's the way it looks. What they would do, they would fire the hydrogen into the air, and it was they put a little the hydrogen flame is invisible, so they put a little oxygen in there at the exhaust so that it would flare and you could see the flame itself. Now, although that was a good test, sometimes the unexpected did occur. So let's look at that. So here you see firing like it was before. You see it going pretty normally. No, looks like something is happening here. Oh my goodness. They let the hydrogen tanks run dry. Oh, you can't take the coolant out away from it. So you see it now raining molten uranium fuel all over the place. They were ejecting some of the fuel. Does that look like something that you would like to be around? I don't think they would let testing like that occur these days. But anyway, you can see what a somewhat unsuccessful test looked like. Okay, so here's another test. This one, they were having some oscillation problems in the reactor, and they couldn't figure out exactly what was going on. So they put some cameras inside the reactor to see if they could see something. And I want you all to look closely and see if you can see what might have been causing the oscillations. It's a fairly long video, so I'll have a few comments here and there. Just one. Okay, so here's the reactor firing. And we'll switch over to a view inside the reactor. So here's you see all the hexagonal fuel elements there. See if you can see something that might be causing the oscillation. They were, what was happening was instead of all the gas, hydrogen gas going through the holes, some was going along the outside from between the fuel elements. So you can see by the way, the film has been speeded up considerably. This is, I think, about speeded up by like a factor of 20 or something like that. Looks like the reactor's having kind of a bad day. And as it kept going, you see it gets better and better. See some fuel pieces coming out. So anyway, you would not want this to happen on trip to Mars for sure. Okay, so what did the NREES test accomplish? Well, the testing occurred from 1959 to 1973. They did 23 reactor tests. The highest power that they achieved was 4.5 gigawatts. Highest temperature was 2750 Kelvin, which was about 850 seconds of specific impulse. Thrust was 1100 kilonewtons, 850 seconds. Maximum burn time was about 90 minutes. And if any of you are familiar with nuclear reactors, going or anything going up 10,000 kelvins per minute is a pretty aggressive rate of temperature. It really stresses the fuel. And this cost, the NREES test program cost about $2 billion. And you recall, this is $2 billion back in the 1960s. So because of inflation, that would be roughly $20 billion today. But in any case, that translated to about, since there were 23 tests and it was $20 billion, that was roughly $100 million per test, which is a lot of money. So other nuclear rocket programs. Back in the late 1980s, early 1990s, there was what was called a particle bed reactor program. It was codenamed Timberwind, and it had a very high thrust to weight, and it was designed to be used on a ballistic missile interceptor. It was designed to that the interceptor was designed to go from Earth to orbit in 90 seconds. So it was really went up pretty fast. It was a classified program, but it eventually was unclassified and transferred to the Air Force, what they had at the time, Space Nuclear Thermal Propulsion Program. And it was aimed at developing an upper stage for a rocket vehicle, but would not operate within the atmosphere. The first, the Timberwind program, was designed to operate from Earth. And so it had a target specific impulse of about 1,000 seconds, which meant that the fuel had to operate at roughly 3,200 Kelvin. Again, pretty high. The target thrust to weight was 30. The NREES program, it was about 3.5. For the NREES engines, for the space shuttle main engine, it was around 40. So here you have a nuclear system that weighed, that had a thrust to weight ratio of something approaching the space shuttle engine. Kind of an amazing feat. The engine sizes range from roughly 400 kilonewtons to almost 2,000 kilonewtons. And it was programmed, was finally terminated in 1994, prior to full engine testing. So they did do some fuel assembly tests. This is what it looked like. It was, again, a hot bleed cycle, so it was very simple. You see the nozzle, the little small nozzle up above where the exhaust from the turbine went. I spent a lot of time looking for good pictures of the engine. Never been able to find any. This is about the best that I've been able to find. Here's what a particle bed fuel element looked like. You see here, instead of flowing axially like the NREES fuel elements, this one, the propellant comes in. It's got a little diverter, that little orange disc up near the top. It goes down the side. It goes through the particle bed. You've got what they call frits, which are basically porous pipes. So the gas comes in through the side. It's porous in that it allows the gas to go through, but the pores are small enough that it won't let those particles come out. The fuel particles in here, or if any of you are familiar with what poppy seeds look like, they look just about like poppy seeds. So they went through the side, through this particle bed. Then they come out through that yellow, which is the hot frit, again, porous pipe. And then it's directed to the outlet. Very efficient, very high surface to volume ratio. That's how they were able to get such high thrust to weight ratios. So for this program, the testing was done in the late 1980s. They did some zero power critical experiments. These are experiments where you don't really bring the fuel elements up to any kind of a high power level. Keep it at really low, just maybe a few watts, just to measure power distributions and make sure that they can actually make this reactor go critical. Conducted two sets called Pipe 1 and Pipe 2, and they were done in the Annular Core Research Reactor, which is one of our test reactors over here. They had power densities of about 1.5 to 2 megawatts per liter, which was quite low compared to what they wanted. They actually wanted to achieve about 30 to 40 megawatts per liter. And but that's all that they couldn't go any higher in the test reactor that they were using. It got outlet temperatures around 1900 K. They did run into some problems of blockages of those frets, which I mentioned. And they also found out that these engines were susceptible to some thermal instabilities, which were not good either. The Russians also had a nuclear rocket program, which existed between 1955 and 1988. It was split among several laboratories there. They looked at two concepts. One was they developed what was called the RD-410, which was called the A scheme. They also had, it was not really, didn't have a lot of thrust, only about 35 kilonewtons, but it was able to run at slightly higher temperatures than the NERVA. So it had a bit somewhat better specific impulse. And it was very good in that it could run continuously for several hours. And B scheme was a gaseous core concept, but was never developed. And the collapse of the Soviet Union basically ended all that work. And here's some pictures of the engine and the test. Had a kind of an interesting fuel, had basically called a twisted ribbon, sort of like a drill bit, and they were put into a bundle, and gas kind of went along the sides and was heated up. Here's another concept which I like. It's called similar to the particle bed, but it uses what are called fuel rings instead of particles. And it has some nice features in that it can you can make the temperature it has a high surface to volume ratio, but it has it's not susceptible to the thermal instabilities that the particle bed had. And you can actually design it so that the fuel is isothermal along its center line, which is helps the fuel to operate at its maximum temperature and also reduce thermal stresses. And if it does crack, for instance, it generally is not catastrophic. And this is kind of what it looked like. See, it looks like the red is a profile of the fuel, one of those grooves. And you see the temperature up at the top, the solid blue line. That's the center line temperature, and it's constant from the inside to the outside. Current testing, again, $100 million per test. We don't have that kind of resources anymore. Starting to run out of time, so I'm talking kind of fast. We need different facilities to do the testing, and these tests are being done at the Department of Energy and at NASA. So we have a small materials test facility at the Marshall Center here. Very expensive. It's got about uses induction heating to do the heating. It's about 50 kilowatts. Designed for really small elements, just a few centimeters. Can expose it to hydrogen. Uses barometers to measure temperatures and thermal imaging cameras. It is licensed to handle depleted uranium. And this is what it looks like. Pretty small rig, but it does some good work. And here you see one under test. The solid cylinder in the center is where the heating is done. The thing that's glowing is actually what's called a susceptor. It's made of tungsten and basically radiates to that center test piece. There's also the transient reactor test at the Idaho National Laboratory. It's a nuclear test, but again, it can only run fairly small samples. Can do a pulse test, or it can do continuous power tests. Fairly small. And here's the picture of that facility. That's in Idaho, and you can see that Idaho National Laboratory. You can see where it is, where that testing's done. This is what I developed here at Marshall. It was called NTREES, stood for Nuclear Thermal Rocket Element Environmental Simulator. Runs at about 1.2 megawatts. Can run hydrogen through it at high pressures. Can also use other propellants, which if you want to. You can put in arbitrary power profiles. It's got lots of measurement equipment to measure temperatures, flow rates, pressures, what have you. And it is also licensed. And here is what it looks like. The little black box on the center left portion is a control room. The tank where it's the test done is, you can see behind the yellow plastic there. And the induction power supply is underneath. Again, so much to say, so little time. This is what it looked like. See, the red is the test piece. You have an induction coil, induction heater. Gas comes out, and we can look through mass spectrometer to see if you're getting degradation. You've got infrared cameras all over the place. And it can operate at up to about 7 megapascals. Again, its idea is to reproduce the conditions which the fuel element would see if it was in a rocket engine. The only thing it really can't do very well is because the induction heating is a little bit different from fission heating. So we have to play some games there to make things come out to look right. But it's that's the one thing it can't achieve. It can't achieve the power densities, temperatures, and what have you. Here's a test of a fuel piece. You see the coils, and the test piece inside. We start running hydrogen in, comes in from the left-hand side. So it kind of cools down the left-hand side. But as the hydrogen heats up, it stays pretty hot on the right-hand side. So we're trying to make the temperature distribution look right, what the fuel would see. There's one of my colleagues at NASA loading in a fuel element. Here is a test. It didn't go quite so well, but again, we're looking kind of at the end of it, looking end on to the fuel element. Yeah, excuse the shaking. I got a little hyper about this point. Was filming it, so you can see the test piece starting to come apart, and was didn't damage the fuel piece, but didn't damage the facility. The NTREES is designed to allow failures like this. So here's what that fuel piece looked like before the test. Here's what it looked like looking at it during the side during the test, and here's what it looked like after the test. So again, can do these tests with minimal damage or no damage to the facility itself. We did want to do a high temperature test just to see what would happen. Put a graphite element in there, and we got it up to 3,800 Kelvin, which is when the graphite basically sublimed away. No damage to the facility. We could probably run tests at over 4,000 Kelvin if we need to. And looking in from the side ports there, it's like staring at a light bulb from a centimeter away or so. Current programs, currently working with the Department of Energy, their advanced space technologies. The main Space Technology Mission Directorate is based at the Marshall Center here. Would use high assay, low enriched uranium. In other words, this is uranium which is not bomb grade, but it's somewhat better than the uranium that you would use in a commercial nuclear reactor. It's currently being managed. Have contracts with the Department of Energy, the Idaho National Lab, and it's you have about $5 million, which were awarded to BWXT of Lynchburg, Virginia. They are partnered with Lockheed Martin, General Atomics of San Diego, and Aerojet Rocketdyne. And also ultra-safe nuclear technologies in conjunction with Blue Origin, General Electric, and Framatome and Mercurian. So that is kind of for design of a reactor, kind of designed for what would be for a Mars mission. We also have the DARPA, which is a Defense Advanced Research Projects Administration. They have a program currently underway called Draco, which is demonstration rocket for agile cislunar operations. That's going hot and heavy right now. Its goal is to operate basically between Earth and the Moon, and it's to demonstrate a nuclear thermal propulsion system. 18-month program. It's about 12 months into it right now, and one track is to focus on the baseline design of the reactor, and the other is for the spacecraft, which will be incorporating that nuclear rocket. Subsequent phases will lead to design and manufacture ground test of this nuclear propelled spacecraft. And contracts for this program are to General Atomics at $22 million, and Blue Origin in conjunction with UltraSafe for about $2.5 million. So, bottom line, nuclear rocket propulsion is an exciting field of study, and I really enjoyed my time working in it. Nuclear propulsion is crucial if we're going to go to Mars, I believe. And we've come a long way in a short time, but we have a long way to go. Let's go together. So that is that's all, folks. Any questions?
Thank you
Hey,
so
Bill,
much for the talk.
thank you
go
so
on,
much
Tim.
again, Bill. We had one question in the chat from earlier, which was about all tests so far have been conducted with uranium, but there was a question about whether any other nuclear materials had been tested or considered.
Besides uranium, you mean? Like
Besides
plutonium
uranium,
or
yes.
something?
Plutonium or
We have not done.
Yeah.
Pardon?
No, I was going to say plutonium or thorium or anything like that.
No, is the answer.
And
Thorium
simply
is
because that's what the infrastructure's there for, is that the US typically tends to use uranium for nuclear projects.
we can use uranium. That people don't like to use the plutonium. It comes down to not that it's a bad material to use, but politically, it's just we can't use it. It would. It's considered a material that could be used for nuclear weapons, and so they don't use plutonium in there. So
I think it's one of the differences we have in the UK is that we've got so much plutonium floating around that the government's looking for anything that will get rid of it.
This would be a good way to get rid of it, but you'll have to test it over there.
Yeah, Lord, we can't even fire normal rocket engines, let alone nuclear ones. I had a question that I wanted to chase up with, because you mentioned the differences between kind of the mission specs, and there was a question about thrust to weight ratio versus ISP.
Yes.
From what I saw, the actual thrust to weight ratio was relatively low compared to a modern chemical engine. So is that where the benefit is perceived in the mission? Because I would have perceived that thrust to weight ratio was more useful potentially for a launch vehicle rather than for a vehicle that would be used in deep space.
That is true to a certain extent. Of course, the heavier things are, the less acceleration that you can have. So when the orbital mechanics are such that when you would leave to, say, go to Mars, or really anything away from Earth, you would typically put the engine in a somewhat elliptical orbit, and what you would like to do is you would like to fire the engine at perigee, that is at the low point of the orbit. When you do that, you use you want to have your thrust directed in such a way that it's all going in the direction you want. You don't want, if you want to go north, you don't want to point your rocket nozzle east, for instance.
Yeah, sure.
So by firing at perigee, that is at the low point, you don't have any what are called gravity losses, or very few gravity losses. And because gravity losses are basically what you're wasting your specific impulse when you do that. So, but if you're firing in order to get the velocity increment you need takes a long time, then you can't do your thrusting at perigee. You have to start well before you hit perigee and keep firing well after perigee. And so you introduce a lot of inefficiencies in your rocket burn when you do that.
Yeah.
And so
I'm glad we're talking about orbital mechanics, because it came on to another question I had about kind of practical implementations of these engines, in that they're going to be quite massive objects on a spacecraft. And hypothetically on a Mars mission, you'll have people on board. So there'll be some need for a good degree of separation between the reactor and the habitation compartment. Given
Yes.
that, and given the sheer mass of the reactor that would be required to even enable the fissioning of 150 grams of uranium on the way to Mars, that's a big engine. Is that going to have significant detrimental effect on the performance of things like reaction control thrusters? Or would you be having to look at alternative systems to allow the nuclear system itself to supplement the reaction control?
Well, you would have, I'm sure, small thrusters, which would probably be chemical to kind of keep everything directed the right way. Also, the nozzles have gimbals on them, so you can move them a little bit. But typically, the way you would probably want to design things is, while the reactors are very heavy and dense, physically they're not really all that big. I mean, you saw the pictures of the nervous systems; they're not huge systems. And the way you would, obviously you'd have the engine at one end, and then you would have your big hydrogen fuel tanks in the middle, and then your habitat where the people stayed at the other end. So basically what you use is you would get a lot of your shielding from the fuel tanks. You would also need some probably what they call shadow shields, which you only have to shield it in one direction. You don't really need to shield it behind the spacecraft. You only need just a disc or something like that at the top of the reactor, where you would do some of the shielding, and then use the fuel tanks to do most of the other shielding. And,
that makes a lot of sense, because it would also help even out the mass distribution. I've got a couple of questions, but I'm very willing to yield the floor to anyone else who wants to jump in, because I could go all day.
I had a quick question. I was just wondering, like, because with the recent breakthrough with nuclear fusion as well, if there's been any trials with using fusion for rocket engines.
That's true. They're good. Actually, my PhD thesis was on a nuclear fusion engine, and the problem with nuclear fusion is they like to be big. Stars make really great fusion engines if you could harness one. And trying to make fusion work on a small scale is really difficult. There's ITER over there in France, not too far from where you all are. I don't know if you've seen pictures of the size of that facility, but I did see one picture, kind of interesting one time. It's shaped like a big donut, and then inside this donut they had what looked like a little animal, which was just dwarfed by this donut, and it said Brontosaurus. And so it's hard to make these things compact. If you're going to use fusion, while it would make just a dandy rocket engine, if we can't figure out a way not only to make it break even plus a bit, but you also have to make it light and small, reliable, and so yes, we have looked at it, and we would love to have one. You've got some ideas how to make it small, light, compact, reliable. I'm ready to listen.
And let's reach break even before we start considering it.
Yeah. So,
but I think there is interesting field at the moment, because with things like the MAST project in the UK, which are using spheromac reactors rather than tokamaks, there is the potential with dual diverters. There is the option of potentially a future pathway along those lines, which would allow for a smaller reactor. But just the power yields at the moment are so restrictive in the fact that we're producing less than 1% of the power we're putting in. So while it's a great way to hyper accelerate particles, maybe fusion tech, as it stands at the moment, could be more useful in terms of things like a plasma thruster, where we're using perhaps a nuclear fission system to power the fuser to actually use the effects of particle acceleration rather than trying to get all the way to fusion in one jump.
Well, yeah, that's a possibility, but what you generally find is that the thrust is pretty low. I mean, it's not low like it is for say an ion engine, but it's still not very big. And so from a kind of a practical standpoint, it would be hard. You'd have to fire it for a long time. And when I did the research I did was on a mirror machine, and they are somewhat more, it's easier to see how they might work. Again, a Spiramac or a tokamak, the question is, how do you get the plasma out and through a nozzle? There's no obvious way to do that I can see, and that would require some pretty interesting engineering in order to get the plasma out to do that. And also the fact that if you're taking plasma out, it's even harder to keep it the Q above 1. And actually you need Qs in the order of about 5 in order to make these things with all the inefficiencies and so forth to make it something that you could use.
Does anyone else have a question before I dive into some deep neutronics stuff?
Pardon?
I was just offering the floor to anyone else before I ask a question about very niche neutronics.
What about the neutronics?
So I was going to ask, you mentioned the idea of having multiple engines on the back of a potential space vehicle.
Yes.
In order to improve control. In that instance, given things like material buckling concerns for the neutronics side, would that be considering using a shared pressure vessel for multiple cores and multiple nozzles, or would you be looking at having multiple I'll say RPVs, as it were, for each of those thruster units, or would you be trying to use the neutronics from one core to kickstart neutronics for the other cores to provide more systematic stability?
No, you really don't want to do that, particularly because you don't want a lot of crosstalk between them, because you open yourself up to what are called common mode failures when you do that. So you would really want them to be pretty independent, as far as you wouldn't want to put them in a single pressure vessel, because typically if one went bad for whatever reason, you'd probably knock out your others at the same time. So what you want, I mean, you can keep them close together, but you don't want to have too much crosstalk between them, and you would like independent systems. So if one engine goes out, you can use the other two.
Okay.
Okay,
that makes a lot of sense in terms of you're building in like redundancy rather than trying to optimize the weight on that front.
Right.
Okay. And in terms of the design of those RPVs, I know you mentioned that the operating pressure that NTREES could go up to was 7 megapascals, so 70 bar.
Yes.
That's 4 times less than what you would see in a commercial PWR. And obviously you're dealing with hydrogen, so there are reasons for that. In terms of the reactor pressure vessel materials, would you be still looking at sort of the conventional steels with a weld bead stainless steel liner, or would you be looking at alternative RPV technologies?
Well, most kind of baseline on stainless steel. The PWRs, do operate at much higher pressures, but the NERBA reactors were actually operated at about 3 megapascals.
Okay.
So, and most of the baselines that I have been with, some of them go higher than 7 megapascals. when I built, I had so much budget, so I could only use so much stainless steel in my pressure vessel. But since at the time I was doing that, NERVA was kind of what people were talking about, and so I said, well, if it operates at about 3 to 4 megapascals, I'll design my pressure vessel for 7.
Okay.
And that gives some headroom. Now, some of them I've seen designs that go up to maybe 10 megapascals. I haven't seen anything above that.
Okay.
And
so it's still quite interesting that it's using a stainless steel pressure vessel rather than a carbon steel that you would typically see on a PWR, because I imagine actually the validation on those pressure vessels is very difficult with the stainless steel because the procedures don't exist outside of the nuclear thermal propulsion industry.
well, I mean, I guess I can't say I haven't really been in the studies for all this. I haven't really been involved in the pressure vessel.
Fair enough. You can tell that I'm a civil nuclear guy.
Yeah. Yeah. So yeah, I was under the impression though that most PWRs and BWRs for that matter were stainless steel. The ones that I've been involved with.
Most of them are relatively standard steel, but they have a stainless steel inner liner. The stainless steel just doesn't have the long-term crack resistance in terms of exposure to things like chloride ions or contaminants in the water. Boric acid can really generate cause, I can't remember the name, cracking in austenitic stainless steels. I can't remember the mechanism name right now. I do neutronics.
Stress corrosion cracking.
That's the one. Thank you very much. I mainly slept through my 6-month course in nuclear reactor materials. But
yeah, that's true. And so it's but you and I can't say what'll come. They may use a carbon wound pressure vessel to get high. It's again, we're sort of in the early stages of all the design. I would imagine that's something that you're going to be in the trade space as far as what to make the engine out of. Again, the idea is to make it light as you can, and again,
aluminium then we'll be fine.
That's true. It doesn't have quite the pressure capability,
and it tends to like to transmute into other elements under neutron exposure.
It does, and so there's that. But again, one big difference between the nuclear thermal systems and a commercial system is commercial systems. You want something that you would fuel for. So that it operates for a year and a half, 2 years, something like that. These engines operate for a couple of hours.
Yeah, this was a question I was going to move on to, in that your design lives are going to be much shorter.
Right. So you can really do things to the fuel there that you would never want to do if you want the fuel to last for for years. It's much different than if you want it to last for 6 hours.
Yeah. So, and what you're saying is you're not fretting about fretting.
Yes. Yeah, there's not going to be much stress corrosion cracking. Yeah. Plus, you're using hydrogen, and most of what you have is going to be metals.
Yeah.
Hydrogen and metals really get along pretty well.
Well, tell that to the people at the Chernobyl power plant. I was going to say, in terms of that hydrogen exposure, in terms of the fuel pin material, the fuel clad materials, would you be typically looking at what is used elsewhere, so zirconium clads, or would you be looking at something else?
Actually, we wouldn't do it that way at all. In a commercial reactor, you've got fuel pins, with zircaloy and little pellets that go into tubes. what we have are probably going to be either you saw the fuel element. It's like I say, a hexagon. This is kind of the baseline, not necessarily that we do that, but they're hexagonal. And what they have is they have fuel particles in them. You have fuel particles that are embedded in a graphite substrate or something like that. So they're kind of all held together like that. I don't know if you're familiar with the fuel particles and so forth.
I've done a lot of work with TREES fuels.
Yes. So
yeah.
So that's probably what, at least for the, I'm sure for the first reactors, they're not going to use a particle bed or the groove ring concept, but they'll be look like Minerva elements, or at least fairly similar. And so so they'll probably be graphite, although they may be cermet, if you're familiar with cermets.
Yeah, I was thinking that there's been a lot of research into cermet stability recently, so that could have been a way that they go. I suppose we'll never find out what DARPA's doing, though.
Yeah, I think they're doing cermets, I believe, but but they are. The thing about cermets is they tend to be a bit more rugged than graphite elements. They're less susceptible to breaking. Although I have managed to break cermets quite easily in my machine.
Cool, you must be very strong.
The machine does it, not me. But,
no, that's really fascinating. Thank you so much, Bill.
We do have a question from the YouTube as well. So if nuclear thermal rocket reactors use their coolant as propellant, then how do you cool the reactor down quickly enough when you shut the engine off?
Okay, well, again, the propellant is the coolant. You run hydrogen through the reactor, and that's it keeps the reactor cool, and it's also your propellant. Now, when you shut down the reactor, you have you've got some fission product build up, even though it's only for maybe a half hour or an hour. You still have fission product build up, plus you've got delayed neutrons, if that means. And so you end up having to waste some propellant to keep it cool. You basically ramp everything down, and you just kind of waste some propellant while you cool it down. You typically the delayed neutrons are pretty much gone after a minute or so. And so, but during that time, you're still producing pretty decent amount of power. So you've got to take that into account. The fission products, you have to account for. You have to put a little bit of propellant through the reactor to take care of. It's amazing how much energy is produced just by the fission products, even if it's only operating for just a very short time. But it's fairly low. Typically, what we kind of calculated is you need about 3% of your propellant that you did for your burn. You have to allocate for cool down afterwards. So you're wasting about 3% just on the cool down of the reactor.
Right. Thank you so much.
How long you've operated.
Yeah. If there are no other questions, then I think it was a bit longer than expected, but it's great that we got all the questions answered. Thank you so much for your time. Yeah, we'd be glad to listen as well. Thank you so much for the talk, Professor Emrich, and it was really great to have you here. Regarding the talks, we also have one next week and the week after, so stay tuned. Nice. Thank you so much, and that's the end of the talk.
All right. Well, thank you.
Thanks again, Bill.
You bet.